before there were continents, before there were forests, before the first living cell found a way to divide and continue. There was a young Earth turning beneath a sky, unlike the one we know today. Its surface was hot, restless, and still being assembled from the debris left behind by the birth of the solar system. Yet, over immense stretches of time, one of the most important transformations in the history of our planet began almost quietly. Water accumulated. It gathered in low places, condensed from a cooling atmosphere, emerged from minerals, and was delivered in part by ancient rocky bodies arriving from space. The first oceans were not blue in the way we imagine them now. They were chemically different, surrounded by volcanic landscapes, warmed by a young sun, and almost entirely empty of the familiar life that later filled the seas. There were no whales moving through the deep, no coral reefs glowing beneath sunlight, no schools of silver fish turning together, and no shells scattered along beaches. There were only water, rock, heat, minerals, gases, and the slow chemistry that would eventually make the oceans into the greatest cradle of life Earth has ever known. Tonight, we can travel backward through that ancient world without rushing. We can leave the modern coastline behind and follow the story of the sea all the way to its earliest beginnings, when the distinction between ocean and atmosphere was still being written by geology itself. The farther we travel into deep time, the quieter the story becomes, because there were no witnesses to record it. The rocks are our witnesses now, and the chemistry locked inside them gives us fragments of a story more than 4 billion years old. Earth formed roughly 4.54 billion years ago from a disk of gas and dust surrounding the young sun. Tiny grains collided, stuck together, broke apart, and collided again. Over millions of years, these fragments accumulated into larger bodies, and gravity gradually drew them together. The young planet grew through impacts, and some of those impacts were enormous. The energy released by collisions was converted into heat, leaving the early Earth partially or extensively molten in places. Heavy elements such as iron sank toward the center, forming the core, while lighter silicate materials rose toward the surface and eventually became the foundation of the mantle and crust. The planet was not born with a finished surface. It was more like a slowly settling sphere of heat and material, continually rearranging itself. Volcanoes were abundant. The atmosphere was radically different from today's. The sun was younger and fainter. Asteroids and other bodies continued to cross the inner solar system, and somewhere within this turbulent beginning was the raw material that would eventually become the oceans. One of the most enduring questions is where Earth's water came from. The answer is probably not a single event or a single source. Water can be released from minerals inside the planet through volcanic and geological processes, while some water-bearing material was likely delivered by asteroids and perhaps other bodies during Earth's early history. The chemistry of hydrogen provides important clues because different reservoirs of water carry slightly different ratios of hydrogen isotopes. Scientists compare those signatures in ancient rocks and meteorites to understand how Earth's water may have been assembled. The result is a picture of a planet that likely obtained its water through a mixture of internal and external processes. There was no single moment when someone could have looked down and said, "Here are the oceans." Instead, water was gradually becoming a permanent part of the planet as Earth cooled, degassed, and developed a stable crust. As the surface cooled enough for solid rock to persist, volcanic gases continued to rise into the atmosphere. Water vapor was one of those gases. The early atmosphere may have contained large amounts of carbon dioxide, nitrogen, water vapor, and other volcanic gases, with its exact composition changing through time. When temperatures fell sufficiently, water vapor could condense. Rain began to fall onto the young surface, although the nature and duration of those early rains remain subjects of scientific investigation. Imagine an ancient volcanic landscape beneath a thick atmosphere, with clouds forming above dark rock and water gathering in depressions. Rain falls onto newly cooled crust, flows downhill, collects in basins, and then evaporates again. Each cycle transfers water between sky and ground. Over time, enough water accumulates that temporary pools become lakes, lakes become larger basins, and connected lowlands begin to form persistent seas. The first oceans, therefore, emerged through countless cycles rather than a single dramatic filling. Water condensed. It fell. It flowed. It evaporated. It condensed again. Rock weathered beneath the rain, releasing minerals and ions into rivers and shallow basins. Volcanoes continued to contribute gases. The crust changed. New seafloor formed in some places, while older crust was buried or recycled in others. The oceans became not just bodies of water, but chemical environments intimately connected with the rocks beneath them and the atmosphere above them. This connection remains fundamental today. Modern oceans are shaped by weathering on continents, volcanic activity, atmospheric circulation, biological processes, and the movement of tectonic plates. The first oceans established this relationship on an entirely different planet. For a long time, scientists debated exactly when liquid water first existed at Earth's surface. Some of the strongest evidence comes from ancient zircon crystals, especially those found in very old rocks from Western Australia. Certain zircons preserve chemical signatures consistent with interaction between molten rock and liquid water, suggesting that parts of Earth's surface may have been cool enough for oceans much earlier than once believed. perhaps more than 4 billion years ago. These tiny crystals are astonishing time capsules. A zircon can survive erosion, burial, metamorphism, and geological recycling, while retaining chemical information from the conditions in which it originally formed. In a sense, a crystal no larger than a grain of sand can carry a message from a world that existed before any known life. The idea that oceans may have existed so early changes the way we imagine the young Earth. Instead of a planet remaining molten for hundreds of millions of years, we can picture a more complicated process in which cooling and solidification happened relatively early, while volcanic activity and impacts continued to reshape the surface. The planet could have had stable patches of crust and liquid water, even while other regions remained highly active. This does not mean the early Earth was calm. It means that stability and chaos could coexist. A shallow ocean might exist beside volcanic islands. Rain could fall on dark basalt while lava flowed into the sea. Clouds could gather above warm water. Minerals could dissolve from rocks and travel into the ocean. The ingredients for long-term chemical cycles were beginning to interact. The early oceans were almost certainly very different in color and chemistry from the modern seas. Their appearance is difficult to reconstruct because color depends on mineral content, suspended particles, atmospheric conditions, microbial activity, and depth. There may have been large amounts of iron dissolved in seawater because Earth's early oceans and atmosphere were far less oxygen-rich than today. Iron can remain dissolved under low oxygen conditions, and when oxygen later became abundant, much of that dissolved iron reacted and precipitated, producing some of the banded iron formations found in ancient rocks. These layers are among the most remarkable geological records of Earth's changing oceans. They alternate between iron-rich minerals and silica-rich layers, recording repeated changes in the chemical state of ancient marine environments. Picture a shallow Archean sea beneath a hazy sky. The water is warm, perhaps tinted by dissolved minerals and suspended particles. There are no forests along the shore. No grass bends in the wind. No birds pass overhead. Instead, volcanic rocks rise from the water, their surfaces gradually altered by rain and seawater. Beneath the waves, chemical gradients develop wherever hot fluids emerge from the seafloor. The ocean is not empty in the chemical sense. It is full of reactions. Molecules collide, minerals dissolve, new compounds form. Heat moves upward from the crust. Sunlight enters shallow water. Electrical and chemical energy move through gradients. It is an enormous natural laboratory extending around the planet. The ocean floor itself may have been one of the most important environments in the early history of Earth. At mid-ocean ridges, and volcanic regions, seawater could circulate through fractures in the crust, become heated, interact with minerals, and return carrying dissolved chemicals. Hydrothermal systems create strong chemical gradients between hot, mineral-rich fluids and cooler seawater. Modern hydrothermal vents support ecosystems that rely not on sunlight, but on chemical energy, especially through chemosynthesis. These modern ecosystems do not prove exactly how life began, but they demonstrate that the seafloor can sustain complex chemistry and biology without direct sunlight. For the young Earth, such environments provide one plausible setting in which prebiotic chemistry may have been concentrated and organized. Other possibilities focus on shallow pools, mineral-rich shorelines, volcanic ponds, or environments where wet and dry cycles repeatedly concentrated organic molecules. There is no single confirmed birthplace of life. Scientists investigate many possibilities because early Earth contained many potentially useful environments. The oceans were not a uniform soup. They contained countless microenvironments, each with different temperatures, pressures, minerals, acidity, and energy sources. Some places may have been destructive to fragile molecules. Others may have provided exactly the gradients needed for chemical complexity. The first oceans were therefore not merely a background for the origin of life. They were a planetary network of experiments. As the young planet cooled, its crust developed and changed. Plate tectonics may have operated differently from today, and scientists continue to debate when modern-style plate tectonics began. Regardless of the exact timing, Earth's crust was not static. Rock was created, altered, buried, uplifted, eroded, and recycled. The oceans participated in all of these processes. Seawater weathered minerals. Sediments accumulated on the seafloor. Hydrothermal systems altered crust. Eventually, rocks that formed beneath ancient oceans could be lifted onto land, where erosion exposed them to the atmosphere. The modern continents, therefore, contain fragments of ancient seafloors and ancient marine environments. The ocean also began to influence the atmosphere. Water vapor is a powerful greenhouse gas, while carbon dioxide contributes to warming. As Earth's surface cooled and oceans formed, carbon dioxide could dissolve in seawater and participate in chemical reactions involving rocks. Weathering of silicate minerals consumes carbon dioxide over geological timescales, while volcanic activity releases it. The balance between these processes helps regulate Earth's climate. The early Earth may have experienced periods when the sun was substantially fainter than it is today, creating the famous faint young sun problem. Yet geological evidence indicates that liquid water existed surprisingly early. Something must have helped keep the planet warm enough for liquid water. and atmospheric greenhouse gases are an important part of the explanation. This does not mean the early Earth had a simple climate. There may have been periods of intense cooling and perhaps global or near global glaciation, as well as warmer intervals. The geological record contains evidence of ancient glacial conditions, although interpreting the earliest episodes is challenging. The ocean would have responded dramatically to climate shifts. Sea ice could expand. Open water could shrink. Volcanic gases could accumulate in the atmosphere. Weathering could slow or accelerate. Eventually, climate feedbacks could push the planet toward a different state. The oceans acted as both participants and buffers in this system, storing enormous amounts of heat and moving energy around the planet. Even before life became abundant, the ocean was already performing another important role: transporting material. Rivers carried weathered rock from land into the sea. Sediment settled through the water column. Currents moved dissolved substances and particles. Waves eroded shorelines. Chemical reactions transformed minerals. Over immense periods, these processes created layers of sedimentary rock. A simple grain of sand could have an extraordinary journey. It might begin as part of a volcanic rock, be broken down by rain, carried by a river, deposited in a shallow sea, buried beneath later sediments, transformed by pressure, uplifted into a mountain, and eroded again. The ocean is not merely water. It is one of Earth's greatest transportation systems. The first oceans were also the setting for the earliest known life. The fossil record of Earth's oldest organisms is fragmentary, but evidence from ancient rocks indicates that microbial life existed very early in Earth's history. Stromatolites, structures formed through the activities of microbial communities, provide some of the most recognizable evidence of ancient microbial ecosystems. They consist of layered mineral structures produced as microbes trap sediment and influence mineral precipitation. Modern stromatolites still form in a few places, giving scientists living examples of a process that has deep geological roots. To imagine an ancient shoreline covered with microbial mats is to imagine a landscape that looks almost empty, but is actually alive. Those early microbial communities changed the chemistry of their environments. Some microbes used sunlight as an energy source. Others relied on chemical reactions. Different metabolisms developed, each exploiting available resources. Over time, photosynthetic organisms began producing oxygen. At first, much of that oxygen reacted with iron and other reduced substances in the oceans and crust. Only after many of those sinks became saturated could oxygen begin accumulating significantly in the atmosphere. This transition, associated with the Great Oxidation Event around 2.4 billion years ago, transformed Earth profoundly. The first oceans had therefore become the stage for one of the greatest chemical revolutions in planetary history. The Great Oxidation Event was not simply a moment when the atmosphere suddenly filled with oxygen. It was a long and complex transition, with oxygen production, consumption, and accumulation occurring unevenly. The oceans played a central role because they contained enormous reservoirs of reduced iron and sulfur. Oxygen produced by photosynthetic microbes reacted with these materials. Banded iron formations record some of these interactions. As oxygen levels rose, environments that had been comfortable for anaerobic organisms became increasingly difficult for them, while oxygen-using metabolisms gained an advantage. Life changed because the chemistry of the planet changed. It is remarkable to think that the oxygen we breathe today is connected to microscopic organisms living in ancient oceans. Every breath taken on a modern shoreline contains a connection to this deep history. The atmosphere did not always contain abundant oxygen. It was transformed by life, and much of that transformation began in the sea. The first oceans were not just the place where life happened to live. They were part of the machinery through which life reshaped the planet. As oxygen accumulated, new minerals became possible. The color and chemistry of rocks changed. The ocean's redox structure evolved. Some ancient marine environments became oxygenated, while others remained low in oxygen. Eventually, more complex cells emerged. Eukaryotic cells, with internal structures such as nuclei and mitochondria, appear in the fossil record long after the first microbial life. Their emergence opened new evolutionary possibilities. The ocean continued to be the great arena in which these changes unfolded. For billions of years, the majority of life remained microscopic. This is an important correction to the way we often imagine the history of Earth. The oceans were not waiting for dinosaurs. They were not waiting for fish. They were not even waiting for animals. They were already full of microbial ecosystems, chemical gradients, sediments, and evolutionary experiments. The long pre-animal history of the ocean is vastly greater than the time during which large animals have dominated marine imagery. For most of Earth's history, if you had somehow looked into the sea, you might have seen very little with your eyes, even though the water was filled with microscopic life. Eventually, however, the oceans became home to increasingly complex organisms. Around 600 million years ago, during the Ediacaran period, multicellular organisms became more diverse. Then, around 541 million years ago, the Cambrian period began, and marine ecosystems underwent a remarkable diversification. Many major animal body plans appear in the fossil record around this interval, although their evolutionary histories extend deeper into time. the seas became more visibly alive. Arthropods moved across seafloors. Sponges filtered water. Worm-like animals burrowed into sediment. Early predators hunted. Trilobites became abundant. The ocean floor was transformed by movement and feeding. The Cambrian explosion was not the sudden creation of life from nothing. It was an acceleration and diversification of forms that had evolved through a much longer history. The first oceans were already billions of years old by the time animals became abundant. This gives the story a different rhythm. Life did not rush. It experimented for immense stretches of time. Cells evolved. Metabolisms changed. Genes accumulated. Ecosystems developed. Oxygen levels shifted. Eventually, complex organisms emerged. The ocean was patient. One of the most beautiful features of marine history is the relationship between water and life. Water provides a medium in which molecules can move, dissolve, react, and be transported. It stabilizes temperatures because of its high heat capacity. It allows organisms to float, swim, filter, and feed. It shapes coastlines and sediments. It creates gradients that organisms can exploit. The chemistry of water made the ocean an unusually productive environment for evolutionary experimentation. The first oceans were therefore not accidental scenery. They were an active ingredient in Earth's biological history. The seafloor also provided another advantage: minerals. Hydrothermal systems can release iron, sulfur, hydrogen, methane, and other compounds. Mineral surfaces can act as catalysts or templates for chemical reactions. Researchers studying the origin of life investigate how such surfaces might have helped concentrate organic molecules or facilitate reactions. Again, no single mechanism has been proven as the definitive origin of life, but the range of possibilities reveals how chemically rich the young ocean environment could have been. Imagine drifting slowly above an ancient hydrothermal field. The water is dark, but below you rise mineral structures formed by hot fluids emerging from cracks in the crust. Clouds of dissolved chemicals spread into the surrounding sea. No sunlight reaches this depth, yet energy is present in chemical differences. Modern ecosystems around vents show that life can exploit these gradients with remarkable efficiency. In the young ocean, similar environments may have provided energy and chemical building blocks long before animals, plants, or even oxygen-rich waters existed. Then, imagine the opposite environment: a shallow coastal basin beneath sunlight. Waves roll across mineral-rich sediments. Water evaporates in sheltered pools, concentrating dissolved substances. Rain arrives and dilutes them. Wetting and drying repeat. Organic molecules could have been concentrated in such cycles, allowing chemistry to become more complex. The contrast between deep hydrothermal systems and shallow surface environments illustrates why scientists continue to explore multiple origin of life scenarios. The early ocean was not one environment. It was billions of environments connected by water. Over time, the oceans became increasingly connected to the continents. As continents grew and stabilized, rivers expanded their role in transporting nutrients and sediments. Mountain building created new sources of weathering. Ocean currents redistributed heat. The carbon cycle became more complex. Biological activity altered sediment composition. The planet was becoming a coupled system in which atmosphere, ocean, crust, and life influenced one another. Modern Earth is the result of this long feedback network. The first oceans also created the conditions for the eventual formation of marine food webs. Once photosynthetic organisms became abundant, they formed the base of increasingly complex ecosystems. Microbes and algae supported grazers. Grazers supported predators. Dead organisms sank, carrying carbon and nutrients into deeper water. Decomposition returned some materials to circulation. In the modern ocean, this biological pump helps move carbon from the surface toward the deep sea. Ancient oceans developed their own versions of these processes as life diversified. The ocean is therefore a giant memory system. It stores heat, carbon, dissolved minerals, sediments, and biological remains. A molecule of carbon may move from atmosphere to ocean, into a microbial cell, into sediment, and eventually into rock. Millions of years later, geological processes may return it to the atmosphere through volcanic activity or metamorphism. The journey can take unimaginably long periods, yet the cycle continues. The first oceans entered these cycles at the beginning of Earth's long geological history. There is also a quiet mystery in the fact that Earth's oceans survived. The young planet experienced impacts, volcanic eruptions, climate changes, and periods of intense geological activity. Yet liquid water remained a persistent feature. Some water was lost to space, some became locked in minerals, and some moved between reservoirs, but enormous quantities remained at the surface. The exact history of ocean volume is still an active area of research. What is clear is that water became one of the defining substances of Earth. Today, oceans cover about 70% of the planet's surface. They contain almost all of Earth's liquid surface water and provide habitat for an extraordinary fraction of life. But the modern ocean is only the latest version of an ancient system. Its chemistry has changed. Its coastlines have moved. Its temperature has risen and fallen. Its oxygen levels have shifted. Its inhabitants have repeatedly appeared and disappeared. The ocean has survived every one of these transitions. The first oceans would have looked out across a very different planet. The continents were smaller or arranged differently. differently. The atmosphere was unfamiliar. The sun was dimmer. The moon was closer to Earth, producing stronger tides than today. The length of Earth's day was shorter because tidal interactions have gradually slowed Earth's rotation. Coastlines therefore experienced a different rhythm. The young moon's stronger gravitational influence would have contributed to more powerful tides, although the exact ancient tidal patterns depended on ocean basin geometry. Imagine waves moving across a young shoreline under a larger-looking moon, while volcanic islands rise from the water, and the atmosphere carries a hazy glow. The moon itself may have formed after a giant impact between the early Earth and another planetary body, creating a debris disk that eventually became the moon. The timing of the moon's formation was very early in Earth's history. Its presence became important not only astronomically, but geologically. Tides influence coastal environments, sediment movement, and ocean mixing. The Earth-Moon relationship has been evolving ever since. The first oceans therefore existed beneath a sky that contained a much closer moon and a shorter day. The early atmosphere may also have created dramatic sunsets. Volcanic particles and gases could scatter light differently from the modern atmosphere. Dust and aerosols would affect visibility. Clouds would form over warm water and volcanic terrain. There may have been frequent storms. Lightning could provide energy for atmospheric chemistry. Rain would wash minerals from land into the sea. The boundary between sky and ocean would have been constantly active. One of the simplest ways to appreciate the first oceans is to follow a single drop of water. Imagine it forming as vapor in a volcanic plume. It rises into a cloud, cools, and condenses. It falls as rain onto dark volcanic rock. It flows through a shallow channel, dissolving minerals along the way. It enters a growing basin and becomes part of the sea. Sunlight warms the surface. Wind pushes it into a current. It evaporates, returns to the atmosphere, and eventually falls again. Perhaps another molecule remains in the ocean for much longer, circulating through deep water and mineral-rich sediments. Water is constantly moving, yet much of the water on Earth is ancient. Some of the molecules in today's oceans have likely been part of Earth's hydrological cycle for enormous spans of time. The first oceans were also places where chemistry could be separated into gradients. Temperature changed with depth. Pressure increased downward. Oxygen varied by location and time. Minerals entered from rivers and vents. Sunlight faded with depth. Such gradients create opportunities for life because energy can be extracted from differences. Life today thrives along gradients everywhere, from sunlit surfaces to deep-sea vents. The early ocean was filled with gradients before there was life to exploit them. Eventually, life began to transform the ocean itself. Microbes changed the chemistry of water. Photosynthesis produced oxygen. Organic matter accumulated. Mineral precipitation changed. Sediments became biological archives. The ocean and life entered a feedback relationship. Life depended on the ocean, while the ocean increasingly depended on life. This relationship became one of the defining features of Earth. The rise of oxygen also changed the color of ancient minerals. Iron that once remained dissolved began precipitating as iron oxides, creating red and banded deposits. The planet's rocks preserve this chemical transition like pages in a book. Some layers formed in ancient seas, others on land. Together, they reveal that the Earth was not static. It was chemically evolving. The first oceans were central to that evolution. As multicellular life eventually diversified, the ocean became a world of movement. Creatures crawled across the seafloor. Some burrowed. Others filtered particles from water. Predators developed increasingly sophisticated bodies. Shells evolved. Skeletons appeared. Eyes became more complex. The ocean became a place where speed, armor, camouflage, and sensory systems were tested by natural selection. The foundations of many modern marine ecosystems were laid during this long transition. But the first oceans remained beneath all of it. Every reef, every fish, every whale, every shell, every marine predator was part of a much later chapter. The original sea had already spent billions of years shaping the chemistry and geology of the planet. The modern ocean is therefore not a separate thing from the first ocean. It is its descendant. When we look at an ordinary beach today, it is easy to see only the present. Waves arrive and retreat. Sand shifts beneath our feet. Clouds pass overhead. But the shoreline is part of a history far older than any human memory. The water has been here in one form or another for an astonishingly long time. The chemistry has changed. The continents have moved. The organisms have transformed. Yet the cycle of evaporation, rain, runoff, currents, and tides continues. A single wave is brief. The ocean is ancient. The wave exists for seconds, while the basin beneath it may have been evolving for hundreds of millions of years. This difference in scale is one of the most peaceful ideas in geology. Individual events pass quickly, but the larger systems persist. The first oceans teach us to think beyond the scale of a human lifetime. There were times when Earth's oceans froze, or nearly froze. There were times when they became warmer and more stratified. There were periods when oxygen penetrated deeper into the water and periods when oxygen-poor conditions expanded. Marine life repeatedly adapted to these changes. Extinctions reshaped ecosystems, but oceans remained. Even when entire groups vanished, water continued moving beneath the sky. The ocean has witnessed almost every major chapter in Earth's history. It was present when the first crust formed. It was present when the first life appeared. It was present when oxygen transformed the atmosphere. It was present during the rise of complex cells. It was present during the Cambrian diversification. It was present when fish evolved, when reptiles returned to the sea, when dinosaurs walked along ancient coastlines, when mammals entered the water, and when humans eventually built ships and crossed the surface. The first oceans therefore connect almost everything. They connect geology with biology, atmosphere with climate, minerals with life, and deep time with the present. Their story is not merely the story of water. It is the story of how a planet became habitable. And yet, the origin of Earth's oceans still contains unanswered questions. How much water arrived from space? How much emerged from Earth's interior? How quickly did the first stable oceans form? What were their temperatures? What was their exact chemical composition? How did early ocean basins differ from modern ones? When did plate tectonics begin operating in something like its present form? How did the earliest microbial ecosystems interact with the ocean chemistry? These questions remain open because the evidence is ancient, incomplete, and often altered by billions of years of geological activity. The uncertainty is part of the beauty. We are not reading a perfectly preserved record. We are reconstructing a world from scattered clues. A zircon here, an ancient sediment there, a mineral signature in another rock, a chemical ratio preserved inside a crystal, a fossil structure made by microbial activity, a banded iron formation stretching across an ancient landscape. Each clue adds another piece. Sometimes the smallest evidence tells the largest story. A microscopic inclusion inside a zircon can reveal that liquid water existed on Earth more than 4 billion years ago. A layer of iron minerals can reveal changes in ocean chemistry. A tiny fossilized structure can show that microbial communities lived along an ancient shoreline. A mineral in an ancient rock can reveal the temperature at which it formed. The first oceans survive not as a single fossil, but as a scattered collection of geological memories. Tonight, imagine those memories coming together. Far back in time, beneath a dimmer sun, rain falls onto volcanic rock. The water collects in a shallow basin. Steam rises from the surface. Beyond the basin, a volcano glows faintly in the darkness. The ocean is beginning to take shape. There are no trees, no animals, no familiar landscapes. Yet the planet is already becoming something remarkable. The rain continues. Rivers form. Minerals enter the sea. The ocean deepens. The atmosphere changes. The crust cools and breaks. New seafloor forms. Hydrothermal fluids rise through cracks. Chemical gradients spread through the water. Tiny systems of chemistry appear in countless places. Somewhere, perhaps in a warm coastal pool or around a mineral-rich vent, molecules begin participating in reactions that will eventually lead toward biology. We cannot know the exact place where life began, but we know that once life existed, the ocean became its home for billions of years. The sea sheltered early organisms, transported nutrients, buffered temperature, and provided countless environments for evolution. Life changed the ocean, and the ocean changed life. The first oceans were therefore not just the beginning of a body of water. They were the beginning of a relationship. Water connected atmosphere, crust, climate, and biology. It carried materials from mountains to basins, heat from one region to another, and chemical information through ecosystems. It became the medium through which Earth's living system developed. Eventually, continents rose, mountains appeared, rivers became larger, the atmosphere became more oxygen-rich, plants colonized land, animals followed. Yet even after life moved onto continents, the ocean remained central. Rain falling on land eventually returned to the sea. Carbon moved between atmosphere, rocks, and ocean. Nutrients traveled through rivers. Sediments accumulated offshore. The ancient relationship continued. If we could speed up geological time, we would watch continents drift like slow shadows across the surface of the planet. Ocean basins would open and close. Mountains would rise and vanish. Ice would advance and retreat. Sea levels would rise and fall. Entire marine ecosystems would appear, flourish, and disappear. Through all of it, the ocean would remain in motion. That continuity is perhaps the most soothing part of the story. The Earth has changed almost beyond recognition many times, yet the fundamental presence of water has persisted. The ocean is an ancient constant moving through changing worlds. And now, slowly, we can return from the deepest past. The first ocean is no longer a mysterious pool beneath a volcanic sky. It has become the vast, modern sea. Waves roll toward familiar shores. Currents cross enormous basins. Clouds form above warm water and carry moisture toward continents. Rain falls into rivers. Rivers return to the ocean. The ancient cycle continues. Every modern ocean contains echoes of the first one. Its water may carry dissolved minerals whose ultimate origins reach deep into geological time. Its sediments may preserve the remains of organisms separated from us by hundreds of millions of years. Its crust may be created at ridges and consumed at subduction zones. Its chemistry continues to interact with the atmosphere and rocks. The ocean remains a living geological system. When the night is quiet, it can be comforting to imagine the sea from this perspective, not as a place that began recently, but as a system that has been moving for billions of years. The waves outside our awareness are part of a planetary rhythm older than mountains, forests, and almost every species alive today. The first oceans did not know what they would become. could not know that their waters would eventually contain complex ecosystems, coral reefs, giant marine mammals, and creatures capable of studying their own origins. They simply formed as part of the natural evolution of a young planet. Yet from those early waters came an extraordinary chain of events. Chemistry became biology. Biology changed chemistry. Microbes changed the atmosphere. The atmosphere changed the ocean. The ocean shaped climate. Climate influenced life. Life altered sediments. Sediments became rocks. Rocks were lifted, eroded, and returned to the sea. The cycle continued. This is the deeper mystery of the first oceans. It is not simply where the water came from. It is how water became part of a self-changing planetary system. Once the oceans existed, Earth had a medium through which countless processes could interact. The planet became more connected. Imagine one last scene. The ancient sea lies beneath a dark sky. The shoreline is made of volcanic rock. Gentle waves move across the surface. There are no lights anywhere. The moon hangs closer than it does today, casting a faint path across the water. Steam rises from a distant volcanic vent. Clouds drift slowly above the horizon. Beneath the surface, minerals circulate through warm currents. The sea is chemically alive, though no animal yet swims through it. Now let time accelerate gently. The volcanic landscape changes. Continents grow. The ocean becomes more familiar. Microbial mats spread. Oxygen begins to accumulate. New organisms appear. The seafloor becomes crowded. Shells appear. Fish emerge. Reefs develop. Marine reptiles move through the water. Mammals return to the sea. Whales eventually cross the oceans. And still the water moves. Accelerate again, and the modern coastline appears. The sea is blue beneath the morning light. Clouds move across the horizon. Waves arrive and retreat. The ancient volcanic rock is gone, transformed many times over. Yet the water remains. Perhaps some of the molecules in that modern wave have passed through countless ancient environments. Perhaps they once formed vapor above volcanic earth, fell as rain, entered a primitive ocean, moved through minerals, became part of a living organism, returned to the sea, evaporated, fell again, and continued circulating through deep time. Water does not remember in the way we do, but the planet remembers through its rocks. The first oceans are written into those rocks. They are written into zircons that survived billions of years. They are written into ancient sediments, banded iron formations, altered seafloor rocks, and chemical signatures. They are written into the evolutionary history of every marine organism. They are written into the atmosphere we breathe and the climate we inhabit. And so the story of the first oceans is not truly a story about a distant past. It is also a story about the present. Every river still runs toward a sea. Every cloud still forms from water. every wave still carries the rhythm of the same planetary cycle that began when Earth was young. The ocean has changed, but it has never stopped moving. The first sea was perhaps dark, mineral-rich, volcanic, and strange. It may have looked almost completely alien to us, yet it became the cradle of life, the regulator of climate, the great transporter of Earth's chemistry, and one of the most enduring features of the planet. Tonight, as the modern world becomes quieter, you can imagine the ocean stretching beyond the horizon. Beneath its surface are layers of history too deep to see. Below the seabed are rocks that formed before continents looked as they do now. Beneath those rocks is the crust, slowly moving and changing. And beneath everything is the heat of the earth itself. The sea is calm on the surface, but beneath it, the planet is always working. This is how the first oceans began, not with a single dramatic moment, but through cooling, condensation, volcanic activity, geological change, chemical reactions, and the patient accumulation of water. Their exact origin remains partly mysterious, but their influence is undeniable. They gave Earth a new kind of environment. They created countless chemical pathways. They sheltered the earliest life. They helped transform the atmosphere. They carried nutrients. They stored heat. They shaped continents. They preserved memories. And they remain here now. So let the ancient world drift gently into the distance. Imagine the first ocean beneath its unfamiliar sky, quiet except for rain, waves, volcanic rumbling, and the soft movement of water across newly formed rock. There is no need to hurry through this scene. It lasted for millions upon millions of years. The first oceans had no beginning that can be marked with a single line. They emerged gradually, and in the same gradual way, they became the foundation for everything that followed. The sea continues to move tonight. The earth continues to turn. Clouds continue to cross the sky. Rain continues to fall. Rivers continue to travel toward the coast. And somewhere beneath the modern ocean, hidden inside rock and sediment, the ancient story remains. The first oceans are still with us. There is another way to understand the first oceans, by thinking about what was missing from them. Modern seas are crowded with signals of life. We hear waves and imagine fish beneath them, birds above them, forests along the shore, and ships crossing the horizon. The earliest seas had none of that. Their silence was not the silence of an empty modern ocean. It was the silence of a planet before familiar ecosystems had been invented. There were no shells accumulating in vast beds, no bones sinking into deep water, no kelp forests bending in currents, and no coral communities building intricate structures. The sea was already physically immense, but biologically, it was almost entirely unfamiliar. That contrast makes the first oceans one of the most fascinating chapters in Earth's history. The planet had created a huge environment before it had created the creatures we associate with the word ocean. The young Earth was also much more geologically active than the world we know. Heat left over from planetary formation remained trapped inside the planet. Radioactive elements generated additional heat, and the mantle moved vigorously. Volcanoes were common. New crust formed. Old crust was altered. Water circulating through hot rock carried dissolved minerals back toward the surface and into the ocean. This interaction between seawater and the crust became one of the great chemical engines of the planet. Even today, seawater penetrates cracks in the ocean floor, becomes heated, reacts with rock, and returns carrying altered chemistry. The modern process is a quieter descendant of systems that have operated for immense periods. Hydrothermal circulation is especially important because it demonstrates that the ocean floor is not a passive boundary. Water does not simply sit above the crust. It moves through it. Seawater can travel downward through fractures, encounter hot rock, dissolve certain minerals, exchange elements, and rise again. At the surface of a hydrothermal vent, the chemistry can be dramatically different from the surrounding seawater. Hydrogen, sulfur compounds, metals, and other substances may become available as energy sources. In a young ocean, these gradients could have been widespread. They would have created countless small chemical environments, each with its own temperature and composition. The possibility that life emerged around hydrothermal systems has attracted enormous attention because modern vent ecosystems show something remarkable. Life does not always require sunlight. At certain depths, bacteria and archaea can use chemical energy from the environment, supporting entire communities that include larger organisms. These ecosystems remind us that the basic requirements for life are more flexible than the surface of Earth might suggest. A dark ocean floor can still be energetic. A place without plants can still support food webs. A world without sunlight can still be biologically active. But sunlight would have mattered enormously in shallow water. Once photosynthetic organisms evolved, the upper ocean became an enormous energy-collecting surface. Sunlight entered the water and powered chemical reactions inside microbial cells. Those organisms became food for others, and their activity slowly changed the chemistry of the planet. The first photosynthetic systems were not modern plants. They were microscopic organisms with very different cellular structures and metabolisms. Some photosynthesis did not produce oxygen. Others eventually evolved oxygen-producing pathways. This distinction matters because oxygen was not always a normal part of the ocean. The early oceans may have been broadly anoxic, meaning that oxygen was scarce in many environments. Instead of oxygen, Other substances played important roles in the chemistry of the water. Iron, sulfur, carbon, and hydrogen could exist in chemical forms that are unusual in today's oxygen-rich surface environments. As microbial communities expanded, they began changing those conditions. The ocean became a place where biological activity could alter geological chemistry on a planetary scale. The Great Oxidation Event is often described as an atmospheric event, but its roots were deeply marine. Oxygen produced in surface waters interacted with dissolved substances, especially iron. When oxygen encountered reduced iron, the iron could precipitate as oxidized minerals. These minerals settled to the seafloor and became part of sedimentary rocks. The result is a geological record of ancient ocean chemistry. Banded iron formations are therefore more than attractive rocks. They are evidence of a planet gradually becoming oxygenated. Imagine standing on a shoreline more than 2 billion years ago. The landscape would still look foreign. There would be no trees, no grasses, and no flowering plants. The shore might be coated with microbial mats. The sea could contain dissolved iron. The atmosphere would have a different chemical balance. Over the horizon, clouds would gather above a broad ocean. Beneath the water, microbial communities would be performing chemical transformations invisible to the naked eye. Yet those tiny organisms were altering the future of the planet. The world looked empty, but it was undergoing one of the most consequential transformations in its history. The ocean's role in the carbon cycle also became increasingly important. Carbon dioxide could dissolve in seawater, where it interacted with water and minerals. Weathering on land transferred carbon and other elements into rivers, and eventually into the ocean. Biological organisms incorporated carbon into organic matter. Some of that material sank into deeper water and became buried in sediment. Over geological time, carbon could become part of limestone, organic-rich sediments, or other rocks. Later geological processes could return some carbon to the atmosphere. The ocean became a vast regulator of carbon movement. This regulation helped shape climate. Water absorbs and transports heat, while ocean currents redistribute energy from warm regions toward cooler ones. Although the exact circulation of ancient oceans differed from today's, the basic physical principle was already important. A planet with large oceans behaves differently from a dry planet. Water stores heat, evaporates, forms clouds, falls as rain, and moves energy across great distances. The existence of oceans therefore changed Earth's climate system fundamentally. The first oceans also interacted with the newly forming continents through weathering. Rainwater is never completely pure. As it passes through the atmosphere and touches rock, it acquires dissolved substances. Carbon dioxide can contribute to the formation of weak carbonic acid, which reacts with minerals. Rivers carry dissolved ions and sediment toward the sea. This process gradually breaks down exposed rock and transfers material to ocean basins. In turn, the ocean deposits sediments that may eventually become new rock. The boundary between land and sea is therefore a place of constant geological exchange. Over millions of years, this exchange helped create sedimentary layers. Mud settled in quiet water. Sand accumulated near shorelines. Chemical minerals precipitated from seawater. Biological remains became incorporated once life became abundant. Burial compressed these materials. Cementation turned loose sediment into stone. Much of the geological record of ancient oceans exists because of this process. The cliffs and rock formations visible today are often the remains of ancient seabeds. There is something almost poetic about the idea that an ocean can become a mountain. Sediment deposited beneath water can eventually be buried, compressed, uplifted by tectonic forces, and exposed hundreds or thousands of meters above sea level. Ancient marine fossils can therefore be found in places that are now high in mountain ranges. A shell that once rested on a seafloor may eventually sit inside a rock face far above the modern ocean. The journey is so long that it almost feels like the planet itself is turning the pages of its history. The continents were also gradually becoming larger and more stable. Cratons, the ancient stable cores of continents, preserved some of Earth's oldest rocks. Around them, younger rocks accumulated through volcanic activity, sedimentation, and tectonic processes. The arrangement of continents influenced ocean circulation and climate. When land masses joined together, ocean pathways changed. When they separated, new seas opened. The first oceans therefore existed within a changing planetary map. There was no single ancient ocean that looked exactly like the Pacific or Atlantic. Ocean basins formed and disappeared through geological processes. Early seas occupied depressions in the crust, while later plate movements created and destroyed larger basins. Scientists use rocks, magnetic signatures, isotope ratios, and tectonic reconstructions to infer where ancient oceans existed. Some have completely disappeared because their crust was subducted beneath other plates. Their existence survives only through fragments preserved in mountains and geological structures. This is one reason the first oceans are difficult to reconstruct. Oceanic crust is relatively young compared with the age of Earth because much of it is recycled into the mantle. Continents preserve older rocks more effectively. The oldest surviving oceanic rocks are therefore much younger than the planet itself. To understand the earliest oceans, scientists must rely on indirect evidence from continental rocks, minerals, sediments, and chemical signatures. It is like reconstructing an ancient forest after nearly every tree has been replaced, using only a few preserved leaves and the soil beneath them. Zircons are especially valuable because they are chemically durable and can survive geological recycling. Some contain inclusions or isotope patterns that reveal the conditions in which they formed. Ancient zircons with oxygen isotope signatures consistent with interaction with liquid water suggest that surface environments capable of supporting water existed very early. Their existence pushes us toward a picture of a young Earth that cooled more quickly than some older models imagined. This early cooling does not mean that the planet immediately became gentle. Large impacts continued. One of the most important early events may have been the giant collision that produced the Moon. A Mars-sized body is thought to have struck the young Earth, ejecting material that eventually formed the Moon. The impact would have profoundly altered the planet, but it occurred very early, probably within the first 100 million years of Earth's history. Afterward, the Earth-Moon system continued evolving. Tides were stronger because the Moon was closer, and Earth's rotation was faster. Over time, tidal friction transferred angular momentum from Earth's rotation to the Moon's orbit, slowing the length of Earth's day and moving the Moon farther away. The first oceans therefore experienced tides under a different astronomical arrangement. A closer Moon would have produced stronger tidal effects, although the actual height of ancient tides depended on the shape and depth of ocean basins. Tides influence mixing, sediment transport, and coastal chemistry. In shallow environments, repeated cycles of wetting and drying may have concentrated molecules and minerals. This is one reason tidal flats and coastal pools remain interesting to researchers studying the origin of life. The young sun was also different. Stars like the sun gradually become brighter as they age, meaning the early sun emitted less energy than it does today. Yet, Earth had liquid water surprisingly early. This creates the faint young sun paradox. If the sun was significantly dimmer, why did Earth's surface not remain permanently frozen? The answer may involve a stronger greenhouse effect, atmospheric composition, cloud behavior, and other climate feedbacks. Carbon dioxide and methane are among the gases that could have contributed to warming. The early atmosphere may therefore have compensated for the weaker sun. This relationship between sunlight and atmosphere was not static. Volcanic emissions changed atmospheric composition. Weathering removed carbon dioxide. Biological activity eventually became another major influence. The ocean absorbed gases from the atmosphere and returned others through evaporation, chemical reactions, and biological processes. The climate system was becoming increasingly interconnected. One can imagine the early ocean beneath a thick atmospheric haze. The sun appears as a softened disk through the atmosphere. Rain falls in warm sheets across volcanic islands. Steam rises from black rock. Rivers are short and turbulent because landscapes are being rapidly reshaped. The sea is warm and chemically active. No horizon is familiar, yet the physical cycle is recognizable. Water rises, cools, falls, flows, and returns. Over time, coastlines became more complex. Rivers built deltas. Sediment accumulated in shallow basins. Volcanic islands merged with other landmasses or disappeared beneath the sea. Waves eroded cliffs. Storms rearranged shorelines. The ocean repeatedly built and destroyed beaches, shelves, and shallow habitats. These environments would later become important for life because shallow water combines sunlight, minerals, and interfaces between land and sea. The earliest life may have emerged in environments that exploited exactly these interfaces. The boundary between water and rock offers gradients in chemistry, temperature, and concentration. The boundary between wet and dry environments offers repeated cycles that can concentrate molecules. Mineral surfaces can provide catalytic properties. Sunlight provides energy. Hydrothermal systems provide chemical energy. Early Earth contained many possibilities. The question of life's origin remains open because chemistry can produce many complex molecules without necessarily producing life. Life requires not just organic compounds, but systems capable of maintaining themselves, storing information, reproducing, and evolving. Researchers investigate RNA-like molecules, metabolic networks, membrane formation, mineral catalysis, and other possibilities. The first oceans provided the water in which these components could interact. One intriguing possibility involves protocells, simple membrane-bound compartments that could separate internal chemistry from the surrounding environment. Modern cells depend on membranes to maintain chemical gradients. Primitive membranes may have formed spontaneously from certain types of molecules. If such compartments could concentrate useful reactions, they might have provided a step toward more organized chemistry. The ocean could therefore have been filled with tiny, transient compartments long before true cells evolved. Another possibility involves mineral surfaces. Certain minerals can attract and organize molecules, potentially bringing reactants together. Clay-like minerals, metal sulfides, and other surfaces have been studied as possible catalysts or scaffolds. Again, no single mineral has been proven as the missing bridge to life, but the diversity of ancient ocean chemistry makes these hypotheses plausible areas of research. What is certain is that once life appeared, evolution began. The first organisms were probably microscopic, and simple compared with modern cells. But even simple life can be extraordinarily adaptable. Microbes can survive extreme temperatures, acidity, salinity, pressure, radiation, and chemical environments. Modern extremophiles demonstrate how broad the possible range of life can be. The young Earth may therefore have hosted organisms in environments that would appear hostile to us. Deep ocean vents are a perfect example. Modern vent communities thrive in darkness under enormous pressure. Their existence tells us that sunlight is not a universal requirement for ecosystems. If ancient life originated in a similar environment, it could have existed long before oxygen-rich atmospheres or complex surface ecosystems developed. The ocean's depth also provides protection. Water absorbs radiation and can buffer temperature changes. The early surface of Earth may have experienced intense ultraviolet radiation because the ozone layer did not yet exist in anything like its modern form. Organisms living underwater would have been partially protected. This makes the ocean a particularly important refuge during the early history of life. As photosynthesis expanded, however, surface waters became increasingly important. Microbial communities captured sunlight and produced organic matter. Some eventually produced oxygen. The resulting chemical transformation altered the ocean and atmosphere. The rise of oxygen also created a new energy source for life, because aerobic respiration can release much more usable energy from organic molecules than many anaerobic pathways. This helped support larger and more complex cells. The emergence of eukaryotes was another major transition. These cells contain internal compartments and complex structures. One of the most important events was endosymbiosis, in which one cell incorporated another and eventually developed a permanent partnership. Mitochondria are thought to descend from ancient bacteria that became symbionts inside early eukaryotic cells. In photosynthetic lineages, chloroplasts have a similar evolutionary origin. The modern diversity of complex life therefore contains echoes of ancient microbial partnerships. All of this happened within oceans that had already existed for billions of years. The sea was ancient even before complex cells appeared. It had survived geological upheavals, climatic changes, and shifts in atmospheric chemistry. Its persistence gave life time to experiment. Eventually, multicellular organisms emerged. At first, many were simple and soft-bodied, leaving few fossils. Later, skeletons and shells became more common, greatly improving the fossil record. The Cambrian seas became populated by diverse animals with different body shapes and ecological strategies. Predation intensified. Burrowing changed the seafloor. Organisms began interacting in increasingly complex ways. The ocean floor itself changed from a relatively quiet microbial surface into a dynamic biological landscape. Burrows disturbed sediment. Feeding organisms moved particles. Predators searched for prey. Filter feeders extracted food from the water. Shelled animals created hard surfaces. The ecological engineering of marine animals began to reshape sediments and nutrient cycles. Yet even in the Cambrian, the ocean remained profoundly different from today. There were no modern whales, no seals, no sea turtles, and no kelp forests as we know them. The dominant organisms belonged to lineages that have changed enormously or disappeared entirely. Trilobites were among the most recognizable. Their segmented bodies and compound eyes made them successful across many marine environments. Their fossils now provide a window into ancient seafloors. As geological time continued, marine ecosystems repeatedly transformed. Fish evolved jaws, vertebrates diversified, reefs expanded and collapsed. Predators became larger and more specialized. Plants eventually colonized land, altering erosion and nutrient delivery to the sea. Forests began influencing river systems. The ocean and continents became even more tightly linked. When forests appeared on land, rivers began carrying new types of organic material and nutrients toward the sea. Plant roots stabilized soils, changed weathering patterns, and affected sediment transport. Later, flowering plants would transform coastal environments again. The ocean's history cannot be separated from the history of land because material constantly moves between them. During mass extinctions, marine ecosystems sometimes suffered enormous losses. The end Permian extinction, for example, devastated marine life. Yet oceans recovered and diversified again. The end Cretaceous extinction removed many marine groups as well as terrestrial dinosaurs. Again, the sea persisted. Life returned to empty ecological spaces. The persistence of oceans through these crises is remarkable. The water itself is not immune to change, but the planetary system is resilient. Temperatures shift, oxygen levels change, currents reorganize, species disappear, new species evolve, the ocean continues. Eventually, mammals entered marine environments in a major way. Early whales evolved from terrestrial ancestors and gradually adapted to life in water. Their story is an extraordinary reminder of how evolutionary possibilities can emerge from ancient ecosystems. A land mammal lineage eventually produced animals capable of living entirely in the sea. Later whales became some of the largest animals Earth has ever produced. Looking at a modern whale moving through the ocean, it is difficult to imagine that its distant ancestors once walked on land. Yet their story connects directly to the ancient sea. The ocean is not simply where marine life began. It is also a place which terrestrial lineages have repeatedly returned. Humans eventually entered the story much later. We built boats, crossed coastlines, mapped currents, extracted resources, and studied the chemistry of seawater. Only recently have we developed instruments capable of seeing the deep ocean in detail. Much of the seafloor remains poorly observed compared with the land surface. In a sense, the modern ocean still contains unexplored worlds. This is fitting because the first oceans themselves are partly unexplored. Their physical remains are incomplete, and their earliest chemistry must be inferred. The deep sea and deep time share a strange similarity. Both are difficult to observe directly. Both contain hidden structures, and both require indirect evidence. Scientists can lower instruments into modern hydrothermal vents and observe ecosystems in darkness. They can analyze minerals from ancient rocks and infer conditions billions of years ago. They can compare isotope ratios, simulate climate systems, study mineral chemistry, and reconstruct ancient continents. Each method provides another view of the same ancient problem. The more evidence we gather, the more sophisticated the story becomes. The first oceans were probably not simply one global blue sea appearing all at once. They were a changing collection of basins, pools, shallow seas, volcanic waters, and deeper environments, gradually connected and transformed. Their chemistry varied from place to place. Their temperatures varied with depth and geography. Their composition changed as the atmosphere and crust evolved. This complexity is important because it gives us a better understanding of how life could begin. There was no need for one perfect environment across the entire planet. Life could emerge from interactions among many environments. Molecules could form in one place, travel to another, become concentrated somewhere else, and eventually participate in a system capable of self-maintenance. Water made this movement possible. It carried molecules and minerals. It created gradients. It connected environments. It transported heat. It provided the medium for chemical reactions. The first oceans were therefore a planetary network. If we could shrink ourselves to microscopic scale and drift through an ancient drop of seawater, we would see a universe of chemistry. Ions would move through the water. Mineral particles would collide. Organic molecules would form and break apart. Temperature would vary around microscopic surfaces. Electrical charges would influence interactions. There would be no silence at this scale, even though there was no sound we could hear. The water would be active with molecular motion. This microscopic world existed long before eyes evolved. It existed before animals could sense it. The ocean's first inhabitants were molecules and minerals interacting under physical laws that had been operating since the beginning of the universe. That thought can make the history of the ocean feel almost timeless. The water was assembled from atoms forged in stars, brought together into a young planet, cycled through atmosphere and rock, and eventually incorporated into living systems. The hydrogen in water is ancient beyond imagination. Much of it originated in the earliest stages of the universe, while oxygen was forged later inside stars and dispersed into space. The ocean is therefore made from materials with different cosmic histories that eventually became one substance on Earth. The story of the first oceans is consequently both planetary and cosmic. Earth did not create its elements from nothing. It inherited them from previous generations of stars and from the material surrounding the young sun. The oceans are a local expression of a much larger cosmic history. Still, the sea itself became uniquely terrestrial. It responded to Earth's gravity, atmosphere, geology, and climate. It developed its own chemistry. It became the environment in which life transformed from simple chemistry into biology, and then into ecosystems capable of changing the planet. When you think of an ocean now, you might imagine a blue horizon beneath a bright sky. But the first ocean may have been dark, hazy, mineral-rich, and surrounded by volcanic terrain. It may have contained dissolved iron and very little oxygen. Its shorelines may have been black basalt and newly formed sediment. Its skies may have been clouded with volcanic gases. The moon may have appeared larger. The day may have been shorter. The sun may have been dimmer. And yet, beneath that strange surface was the beginning of everything we recognize as a living planet. There is no single fossil of the first ocean. There is no ancient shoreline preserved perfectly. There is no photograph. Instead, there are fragments. A zircon, a mineral, a sediment layer, a chemical ratio, a microbial structure, a piece of ancient crust. Together, these fragments allow us to reconstruct a world that existed long before memory. Perhaps the most remarkable fragment is the fact that the ocean is still here. We do not need to imagine an entirely vanished environment. We can stand beside the modern sea and know that we are looking at the descendant of those first waters. The chemistry has changed, the organisms have changed, and the continents have moved, but the fundamental cycle continues. A drop of rain falling tonight may eventually reach the ocean. A wave forming tomorrow may evaporate and become part of a cloud. That cloud may cross a continent and fall as snow. The snow may remain frozen for years or centuries, then melt into a river. The river returns to the sea. The cycle is continuous. This continuity is perhaps the best ending for the story. The first oceans were not a separate chapter sealed away from the present. They were the beginning of a process that is still happening around us. The ocean still gathers heat from the sun. It still exchanges gases with the atmosphere. It still receives minerals from rivers. It still creates and destroys sediments. it still hosts microbial ecosystems. It still contains deep regions where sunlight never reaches. It still hides geological structures beneath its floor. And it still carries water through a cycle that began on a young Earth. Tonight, if you imagine the sea beyond the darkness, you can imagine it on two timescales at once. On the surface, waves rise and fall over seconds. Beneath them, currents move over days, years, and centuries. Deeper still, sediments accumulate over thousands and millions of years. Beneath the sediments, tectonic plates move over millions of years. And beneath the crust, the mantle circulates over even longer periods. The ocean is therefore part of a layered clock, with many rhythms operating simultaneously. The first oceans began on that deepest clock. Their formation was slow enough to be invisible to any observer who might have existed. No creature stood on a shore and watched the first sea arrive. There was no first wave that anyone could identify. Water simply accumulated until oceans became a permanent part of the planet. That is what makes the beginning so peaceful. It was not an event that needed to be witnessed. It was a process. Rain fell, water gathered, rock weathered, minerals dissolved, volcanic gases rose, the atmosphere changed, the crust cooled, the sea deepened. Life eventually appeared, and the ocean carried on. From there, billions of years unfolded. The sea became the setting for evolution's earliest experiments. Microbes altered chemistry. Oxygen transformed the atmosphere. Complex cells emerged. Animals diversified. Ecosystems developed. Life moved onto land and returned to the sea. Continents rearranged. Climate shifted. Extinctions came and went. Through all of it, the ocean remained. Perhaps that is why the first oceans are such a comforting subject for a sleep documentary. Their story moves at a scale far beyond ordinary urgency. There is nothing to solve tonight. We can simply observe the planet becoming what it is. The changes are slow. The processes are patient. The evidence is quiet. Imagine the young Earth one final time. A dark volcanic coastline stretches beneath a hazy sky. Warm rain falls into the sea. Waves roll across newly formed rock. Steam rises where seawater meets hot ground. The moon hangs closer than it does today. There are no cities, no roads, no forests, and no voices. There is only the sound of water and the distant movement of the planet beneath the surface. Below the waves, minerals circulate through ancient currents. Farther down, hot fluids rise from the crust. In shallow water, sunlight enters a world that has not yet become crowded with life. The ocean is waiting, although it does not know what waiting means. It simply exists, and over unimaginable time, it changes. The first cells appear. The first microbial communities spread. Photosynthesis begins to reshape the chemistry of the sea. Oxygen accumulates. new forms of life emerge. The ocean becomes increasingly complex. Eventually, creatures with shells crawl across its floor. Fish swim through its waters. Reefs rise. Predators appear. Marine reptiles move through ancient seas. Whales return to the water. And much later, humans stand on beaches and look out across the same planetary system. The distance between the first ocean and the modern ocean is almost impossible to imagine, yet the connection is direct. The water did not need to become something entirely new. It only needed to continue moving. That is the quiet secret of the sea. It changes constantly, yet remains. The first oceans were almost completely alien to us, but they were also the beginning of a world that eventually became our home. And now, the ancient journey can become quiet. The volcanic horizon fades. The young moon becomes a distant light. The rain softens. The first ocean stretches into darkness. Billions of years pass like a slow breath. The continents form and drift. The atmosphere changes. Life expands. The sea continues. And tonight, beneath the modern sky, waves still arrive at the shore. Perhaps that is the most beautiful connection of all. The first ocean is gone in its original form, but the ocean itself remains. Its waters still move beneath clouds. Its currents still cross the planet. Its depths still hide places untouched by sunlight. Its sediments still collect fragments of the present. And its history still reaches backward to the earliest chapters of Earth. The sea has been here almost as long as the planet has been able to hold it. It has carried the chemistry of mountains into basins. It has carried heat across hemispheres. It has carried life through evolutionary time. It has carried carbon between atmosphere and rock. It has carried the memory of vanished worlds into sediments. And it continues carrying the present toward the future. So when you picture the first oceans, do not picture only a strange ancient sea. Picture the beginning of a planetary rhythm. Water rising, water falling, water flowing, water gathering, water moving through rock, water moving through life, water returning to the sky, and water returning again. The rhythm is still happening. The same earth that once cooled beneath a young sun still turns beneath us. The same planet that gathered its first oceans still carries seas across its surface. The same water cycle that began billions of years ago continues tonight. And somewhere in the darkness, beneath the surface of the modern ocean, ancient chemistry is still being written into new sediments. The first oceans were the beginning, but they never truly ended. They simply became the oceans we know. There is one final scale at which the first oceans become even more extraordinary, the scale of time itself. A human life is measured in decades. A civilization may endure for centuries or millennia. A mountain range can exist for millions of years. An ocean basin can open and close over hundreds of millions of years. The first oceans belong to a scale where even entire geological eras become chapters. When we say that liquid water may have existed more than 4 billion years ago, we are not describing a distant historical period in the ordinary sense. We are reaching toward the beginning of the planet's visible geological memory. Almost every familiar feature of Earth had yet to appear. The continents were not arranged as they are now. The atmosphere was not the atmosphere we breathe. Life had not yet developed the complexity that would eventually cover the planet. Yet, water was already present, moving through the same basic cycles that still connect sky, land, and sea. This deep perspective also changes how we think about stability. The ocean feels permanent because it is larger than anything we can experience directly. A coastline may look unchanged from one day to the next, but geological forces are constantly working beneath it. Waves remove grains of sand. Rivers deliver new sediment. Currents redistribute material. Tectonic plates move beneath the ocean floor. New crust forms at spreading centers, while old crust sinks back into the mantle. The sea is therefore never truly still. It only appears still when viewed from a human timescale. The first oceans were even more dynamic because the young planet was hotter, volcanically active, and undergoing rapid geological development. The deep sea today offers a small glimpse of that ancient dynamism. Hydrothermal vents create towers of mineral deposits on the seafloor. Warm fluids rise through cracks. Cold seawater descends around them. Chemicals mix. Minerals precipitate. Microbial communities thrive. These environments remind us that the ocean floor is alive with physical processes, even where sunlight never reaches. The first oceans may have contained many more such systems because the early crust was more active and the planet's internal heat was stronger. The boundary between ocean and Earth was therefore a place of continuous exchange. And perhaps this is the most important lesson of all. The ocean did not merely sit on top of the planet after Earth formed. It became part of the planet's internal conversation. Water entered rocks and returned. Minerals entered water and settled again. Gases moved between sea and sky. Heat moved between crust and ocean. Life eventually joined the conversation and changed it forever. The first ocean became a participant in Earth's evolution. If we could somehow watch 4 billion years pass in a single night, the changes would seem almost impossible. The young volcanic planet would gradually acquire continents. Microbial mats would spread across shorelines. Oxygen would begin altering the atmosphere. New cells would appear. Oceans would change color and chemistry. Ice would advance over enormous areas and later retreat. Continents would assemble and break apart. Life would repeatedly diversify and disappear. Fish would evolve. forests would reach the land. Dinosaurs would arrive and vanish. Mammals would expand. Whales would return to the sea. Humans would finally appear and begin asking how it all started. Yet, beneath every scene would be water. That continuity gives the ocean a quality that is difficult to describe. It is ancient without being frozen in the past. It carries old chemistry while constantly receiving new material. It preserves evidence while erasing other evidence. It creates habitats while destroying others through storms, currents, and changing sea levels. It is both archive and eraser. The first oceans were therefore not simply the beginning of marine environments. They were the beginning of one of Earth's great memory systems. Sediments buried beneath the seabed record ancient climates, biological activity, volcanic eruptions, ocean chemistry, and changes in sea level. Scientists extract cores from the seafloor and red layers that accumulated long after the first oceans formed. In some cases, microscopic fossils reveal ancient temperatures. Isotopes reveal chemical conditions. Dust reveals past atmospheric circulation. Volcanic ash layers provide dates. The ocean floor becomes a chronological archive. Yet, even the archive has limits. Oceanic crust is recycled. Deep sediments are buried. Plate tectonics destroys some records while preserving others. The oldest pages of the ocean's history have mostly disappeared. That is why the first oceans remain partly mysterious. We can reconstruct them, but we cannot recover them completely. Perhaps that uncertainty is exactly what makes the subject so compelling. There is enough evidence to know that early seas existed, but not enough to remove every question. We can see the outline without seeing every detail. We can understand the process without knowing every location. We can identify the broad chemical changes without knowing precisely what the first waters looked like. And that is enough to let the imagination travel. Picture the first shoreline again. Dark rocks descend into warm water. The atmosphere is hazy. Clouds gather above the sea. A storm approaches from the horizon. Lightning flickers within the clouds. Rain begins to fall. The water on the rocks becomes connected with the water in the ocean. Minerals dissolve. Small channels form. The sea receives another pulse of material from the land. Nothing dramatic needs to happen. No creature needs to appear. The planet is already becoming alive in another sense. It is developing cycles. It is developing feedbacks. It is developing the chemical stability that will eventually allow biology to flourish. The first oceans are therefore a story about preparation as much as origin. They prepared a world in which life could persist and evolve. They moderated temperature. They transported nutrients. They created chemical gradients. They protected molecules from radiation. They provided countless habitats. And once life emerged, they gave it a vast environment in which to diversify. The The sea became Earth's great evolutionary laboratory. For billions of years, it experimented with forms, metabolisms, and relationships. Most of those experiments left no obvious trace. Some lasted only briefly. Others produced lineages that survived for hundreds of millions of years. The ocean repeatedly tested what life could become. Today, when we look across a calm sea, we see only the latest version of that experiment. Beneath the surface are organisms descended from ancient lineages, microorganisms carrying chemical strategies developed long ago, and sediments that slowly accumulate the evidence of the present. The modern ocean is still evolving. The first oceans would not recognize today's sea, but they would share its fundamental identity: water moving through a changing planet. That may be the simplest way to end our journey. The first oceans were born from a young Earth that was cooling, changing, and finding equilibrium. Water gathered through processes that remain partly mysterious. Rain fell. Volcanoes released gases. Minerals entered the sea. The crust evolved. The atmosphere changed. Life appeared. Life transformed the chemistry of the water. The ocean transformed life in return. Billions of years later, the relationship continues. The sea still touches the atmosphere. The atmosphere still feeds the sea. The land still sends rivers toward it. The crust still moves beneath it. Life still changes it. And the ocean still changes life. So let the modern sea become quiet in your imagination. Let the horizon fade into darkness. Beneath the surface, currents continue their slow journeys. Far below, cold water moves through deep basins. Even deeper, the crust rests above the hot mantle. Somewhere along a distant ridge, new oceanic crust is forming. Somewhere else, old crust is disappearing beneath a tectonic plate. The planet is still working, but nothing needs to happen quickly. The ocean has never needed to hurry. It formed slowly. It changed slowly. It carried life slowly. It recorded history slowly. And it continues into the future at the same patient rhythm. The first oceans were almost completely alien. Yet they were also the beginning of the familiar blue world outside our windows. The water is ancient. The movement is ancient. The cycle is ancient. And the story is still unfolding.